Okay, so the problem we're going to be working on here is this little example of a member that an object that is simply supported on these two ends, A and C here. And then it's midway through the span, it's got this other beam that it's connected to that hangs down to. Then it's connected to another beam here, and then on the ends of that beam is a pair of forces applied. 10 kip that are applied to either side in opposite directions. So we can, now that we've got our kind of simplified representative structure drawn down here, move on to our free body diagram. And yeah, just replace the supports with the respective forces that would be involved in there. So in this particular instance, we do have a reaction at both supports. Pair reactions at both supports, since those are both pinned at both pin connections there. So we're going to have forces with a y and x component on either side. And then obviously on our free body diagram, we also include the plus and minus 10 kip forces. Now, how to go about solving this? Well, to start off, we need to realize that the 10 kip force there is a moment couple, which we can replace with a moment, either on the diagram or just in our when we're doing our calculations. It'll have a magnitude of 20 kip feet. And that'll be in the positive z-axis, since this particular couple was acting to impose a counterclockwise movement on this structure. So moving on over, I'll go about solving for our reactions using our equilibrium equations. First thing I'm going to do is I'm just going to take a moment about the point C, so that's the corner right here. The sum of our moments, well, we got the 20 kip that we started with, and the only other force on here on this diagram that will cause a moment when measured about C is going to be our FYA here, because everything else either everything out the line of action for all the others pass through the point C. So all that stuff, all those others are zero. That allows us to have the sum of our moments as the 20 kip feet minus 8 feet crossed with the FYA. That's minus 8 feet because the vector from this point C to the point where the force is acting is negative, because we're defining our axes as positive. You know, x-axis is positive in the right way, and then obviously y is positive upwards. Next, so we can use that to solve for FYA here. That'll give us 2.5 kips. Next thing we need to know is what the FYC here is. Well, take the sum of our forces in the y direction. We've only got the two of them. We've got FYC and FYA. So add those two together, they equal 0. Therefore, if FYA needs to be have the same magnitude in the opposite direction as FYC does, which means that we can solve for FYA as which means we can solve for, I made a mistake on my page here, which means we could solve for FYC. I mixed up the A's and C's here. FYC is going to be negative 2.5 kips. The reactions in the x components here, we know that they're equal to 0, so therefore they need to be equal and opposite. It's kind of going on down. Like, one thing we can do is we can kind of take this span here, and we can conceptually think of it. Realistically, that span there could be replaced for the purposes of finding out what's going on there, just as a single beam with a moment applied in the middle, and then supported on other sides. Now, a system like that will, at this point, it is indeterminate. If we have replaced one of these with a roller connection, then obviously, then just everything would be equal to 0. But essentially, if you're holding a stick in place on either side, and you're also trying to twist it, the only reactions that need to happen are the y components of those. If all you're doing is trying to twist it, you're not going to be causing any significant lateral movement, other than possibly a little bit that might happen just due to this, the minor stretches that occur when you're twisting. But the lateral any lateral displacement or lateral forces generated are going to be negligible. So we can kind of just say that that's equal to 0. This allows us to basically finish off our free body diagram overall. So now we move on to essentially going to our loading diagrams. So again, axial load throughout is going to be negligible. There's no forces here that are going to be generating axial loads. Likewise for torsion. Shear diagram is fairly simple. On this top beam here, we've got we've got a positive. We've got a we got a positive shear force applied on the one end, and that remains undisturbed until we get all the way over here. So that's just a constant shear force in over the length of this span. Same idea happens at the bottom edge, except obviously, starting from the left and moving right, we've got a negative shear force applied, so that'll give us a negative internal shear load across this span. So we've also got the bending moment diagram that we need to do. So that is kind of based upon a combination of the shear diagram. Let's make my face a little smaller there. There we go. Combination of the shear diagram and kind of the point bending moments that are applied to these two beams by the reaction from this one that's connecting them. So basically this beam in the middle, its only purpose is to basically kind of move that 20 kip foot moment from one point to another. That also means that the loading on that particular beam there is fairly simple. It has a constant 20 kip foot bending moment throughout its length. It doesn't have any shear within it, so that means that the bending moment is constant across that beam, and it doesn't have any axial torsional load either. So it's just its entire purpose is to transfer the bending moment from the two beams that it's connected to. And that point can be seen if we kind of look at I turned this thing on its side, so we're looking at the beam in question. And if we kind of look at a free body diagram here and do a bit of simplification, we're taking this couple here, replacing it with an equivalent moment, and we take this couple here, replace it with an equivalent moment, apply it at either end, and essentially here we've got the two moments on either side of that beam in the middle that is applied to it by the other two beams. Likewise, thanks to Newton's third law, it's applying an equal and opposite moment to the beams in question. So at this point in the on the diagram, it is, if we erase this middle beam, then we're getting that. And if we erase the middle beam for the bottom one, we are getting this. So we can have separate free body diagrams for each of the three components as well, and that can help us determine how the bending moments change. But so we know that the because we have a positive shear here, we know that the bending moment's going to be increasing as it the bending moment there is going to be increasing as we move along the beam in the x-axis, and we know that the slope throughout is constant until we kind of get to this point here where we have the the point load attached, drops suddenly, and then continues on upwards until it hits 0 on the other end. So we know this. We know the slopes. We know the slope is based upon this shear here. So we know that based upon the span, it's 4 feet from this point to this point, 2.5 kips. It's going to cause our moment to increase to 10 kip feet. And then likewise, we could work from the other way, from the other end out. It's starting at 0, and going from left to right, it's increasing. So going from right to left, it's decreasing. So it's starting at 0, goes down to negative 10 kip feet, and we see that we have this sudden drop here that is equal to the amount that we expect it to be. That's equal to our 20 kip feet drop based upon the reaction from this guy. So that allows us to complete our bending moment diagram. It's similar idea on the bottom here, except the forces are reversed. So we're starting out with a negative shear load, which means that our bending moment starts at 0, decreases down to 10 kip feet, jumps up, and then decreases down to down at the same rate until it hits 0. So again, since the shear here is negative 10 kips and the span here is 1 foot, then again we're starting from 0, we're getting to negative 10 kip feet fairly shortly. And then again, constant bending moment throughout the middle span. as for the view of the distorted structure, this is what I came up with. The middle section here, that's fairly simple. You know, it's just a constant bending moment, so bends downwards, based upon the fact that the bending moment here that's imposed here is going to go around like that. Likewise, the reaction that needs to happen to ensure that this thing doesn't spin out of control is going to be equal and opposite. So it's going to be bending down on either end, and it's going to be causing kind of that bowing in the middle. So as for the sections at the top and the bottom, well, let's look at the top first. So if we kind of replace, look at just the beam and then this bending moment that's applied by the middle beam. So we got the bending moment. We got the two tops, the two sides there. So essentially, it's going to cause a bending moment diagram that looks like this. The key thing here is that the magnitude of the bending moment is highest in the middle and it's lower at the ends. So what that means is that the curvature will be highest in the middle and it'll be lowest at the ends. So these sections here are going to be relatively straight, whereas in the middle here, that's where we're going to see the highest degree of curvature. So something like this works. It's going to start off relatively straight. It's going to start curving upwards because the magnitude is positive on this side. It's going to keep curving upwards until it hits the middle, where we get the switch from the switch of the signs of the bending moment, and then it's going to start curving downwards. It starts curving downwards as fast as it was curving upwards here. Starts curving downwards, slows down the rate at which it's curving downwards, and then eventually mostly straightens out as it gets near the ends. So these sections are going to be mostly straight. This section here in the middle is going to be relatively bendy. And then so get something like that looks like that here. As for the bottom, well, the free body diagram for the section the free body diagram for the section at the bottom looks exactly the same as the free body diagram as the section at the top, but the signs are reversed. So it shouldn't be all that surprising that essentially what we're going to end up with instead is roughly the same shape, just reversed. So it starts going up, then curves down swifter, slows down, and then straightens up as it goes down. So I didn't mean to do that. We'll get rid of those arrows. And yeah, so that's a very exaggerated version of what the displacement